Hello, in this video we are going to talk about the mean value theorem. So mean value theorem states that if we have a continuous function f on an interval a to b, and if this function is differentiable inside a to b, then there exists a point c in this interval a to b such that the derivative of the function at c is equal to the slope of the line connecting the endpoints. Like this expression here, f of b minus f of a divided by b minus a. This is the slope of the line connecting the endpoints a f of a and b f of b. And then the derivative at c means the slope of the tangent line to the graph of the function at some c. So there must be a point like that which has the same slope as the line connecting the endpoints. Like graphically you can think of it like this. So we have a function here, the left top picture. You have a continuous function here with the dashed line. This is a continuous function. Continuous means no holes, no jumps in the graph. Differentiable, it means that the function goes smoothly. There is no broken graph. Okay, so it just goes smoothly. This is what differentiable means. There is no broken graph here. Then there is a line connecting the endpoints a f of a, this point, and then this other endpoint b f of b. So that line connects these 2 points. These lines connecting 2 points are also called secant lines. But if there is just one line passing through 1 point, that's called a tangent line. If there is a line passing through 2 points, those lines are called secant lines. Anyway, this secant line has a slope, and since the function is continuous and differentiable, it must act like there must be at least a point where the slope must be same as the secant line's slope. Okay, that's what mean value theorem says. This right top picture, like this is another example, visual example. You have a function like this. It goes from this endpoint a f of a to the other endpoint b f of b. It goes continuously, like no jump, no hole in the graph, and then it goes smoothly. There is no broken graph. It just goes smoothly like this. So as you see, the graph of the function must turn around somewhere where it will have the same slope as this line connecting these 2 endpoints, which is this point here, which is shown by this Greek letter psi. It doesn't matter, psi or c. Or look at the bottom picture here. This is another visual example. We have a continuous and differentiable function coming from this point a f of a endpoint to the other endpoint b f of b, continuously and differentiably. Continuously means no hole, no jump. Differentiably means there is no broken graph in that part. So there is a line connecting the endpoints, which is this middle line. It has a slope, and as you see, it has to have at least 1 point, maybe 2 here. Like psi 1 has the same slope like that secant line slope, and also psi 2, the derivative or the slope of the tangent line, also same as the slope of the line connecting the endpoints, which is f of b minus f of a divided by b minus a. This is how we will see mean value theorem graphically. Now, this is another example, but this is more algebraic and numerical. Let's say we have a function f x squared plus 3x plus 1. This is a function defined on the interval 0 to 2. Find a point c in the interval 0 to 2 such that f prime at this point c is equal to f of 2 minus f of 0 divided by 2 minus 0. Here 2 and 0 are the endpoints. So since this function x squared plus 3x plus 1 is a polynomial, and remember all polynomials are continuous and they are differentiable in their domains. So this function x squared plus 3x plus 1, it's continuous on the closed interval and it's differentiable on the open interval 0 to 2. Then what will happen? By the mean value theorem says if you have a continuous and differentiable function, then there must be a point c where f prime at c, which is the slope of the line, slope of the tangent line at c to the graph of f, must be equal to the slope of the line connecting the endpoints, f of 2 minus f of 0 divided by 2 minus 0. So what is f prime first? It's the derivative of x squared plus 3x plus 1, which is 2x plus 3. Now, if we plug c in this derivative, it's going to be 2c plus 3, right? Like it's going to be 2c plus 3. And this must be equal to the slope of the line connecting the endpoints. Now the function is x squared plus 3x plus 1. So plug the first endpoint 2, you are going to get 2 squared plus 3 times 2 plus 1, minus the second endpoint is 0. 0 squared plus 3 times 0 plus 1, divided by 2 minus 0. top is the change in the y values, bottom is the change in the x values. That gives a slope for the line connecting the endpoints. This must be equal to the slope of the tangent line at c, which is 2c plus 3. Now we don't know what c is, but we are going to solve this equation coming from the mean value theorem, and we are going to find that c. Okay, 2c plus 3 equals, 2 squared is 4, 3 times 2 is 6, so we have 4 plus 6 plus 1, minus 0 squared is 0, 3 times 0 is 0 plus 1, which gives 11 minus 1 over 2, that is 10 over 2, which is 5. So 5 must be equal to 2c plus 3. Okay, now we are solving for c because we want to find that c. 2c equals 5 minus 3, take that 3 from the left and take it to the right, it's going to be minus 3, so 5 minus 3 is 2. Well, 2c equals 2, then divide both sides by 2, c equals 2 over 2, which is 1. Now, c equals 1 is the point in the interval 0 to 2 where the derivative is equal to 2 times 1 plus 3 equals 5, which is equal to the f of 2 minus f of 0 divided by 2 minus 0, which is the slope of the line connecting the endpoints. Now, graphically, it's going to look like this. So we have a function here, x squared plus 3x plus 1. We have an interval 0 to 2. So one endpoint is 0 to 1. The other endpoint is 2 to 11. Okay. So there is a line connecting these two endpoints, which is this line. It has slope 5. And then we just have found that there is a point in this interval, which is c equals 1, where the slope is also 5. Okay. So this is an example, but a numerical example for mean value theorem.